If we are all ready, I'll go ahead and start. Good, it might be, oh, it is not quite afternoon yet. Good morning, everyone. My name is Emily Combs. I am also from Liberty University, and I'm working under Dr. Shabayo and Dr. Strasser. And today I will be presenting our current research into the turbulent energy dissipation of a plane turbulent wake after a heated cylinder. So going over just introduction, objections, how we made our model, the results, and then summary and conclusion. But this undergraduate study utilized ANSYS fluent turbulent models to replicate an experiment previously done using numerical methods. The experiment was done by Antonia and Brown in 1986. They used a wind tunnel in order to simulate, well, not simulate, to experiment with a heated cylinder closer to the beginning, and then way down the stream, they took various measurements of heat and velocity at the points. But this research sought to understand the behaviors of the turbulent wake after a heated circular cylinder, so we were kind of following after them. They sought it, and we will search into even further. And we will be comparing the performance of SST, LES, and IDDS models to this experimental data to see which one can better correlate with the experimental data. So the objectives of this study: to model the combination of turbulent flow with heat transfer, to create a methodology for our future research when we dig even deeper, and then just to evaluate the various turbulent computational models with each other. So going into our actual model formulation, starting with our geometry, all of the walls are symmetry, except for the little tiny heated cylinder in the middle. That one is aluminum. And then all of this is normalized according to the cylindrical diameter, which is 2.67 millimeters. And they had a little bit of beginning at the start, and then they took data at 420D past the cylindrical surface. So that would be 440D by that reference. And then currently we have a coarse mesh with 1.05 million nodes. This will be refined later on, but that is not with our current research. Going a little bit more into our mesh, since that is very important for some of the models that we are working with. This mesh has a Y plus value of 2.2. This is good for SST. It recommends less than 10. For the correlation IDDS, it needs less than 5. However, as you see here, whale LES works best around 1. So whale LES requires our more refined mesh that we'll be working on later. So the data extracted from this model may be incorrect, and it will be reflected later on. But going into the actual setup, a little bit about the actual models I'll be using. The shear stress transport, this one averages stuff out, and we have the kinematic eddy viscosity is our first governing equation, with the second one being about the turbulent energy. This will be with a study with the pseudo time set since it averages things. Then we have while adapting local eddy viscosity, large eddy simulation. This is specifically the while adapting is what we used for the LES. This is transient, and you can see that the first equation uses different for the same parameter, but the second equation is now with our shear stress. And this means that the mesh around our cylinder matters a lot, which is reflected. IDDS, specifically using a correlation for around the wall. This one is the improved delayed detached eddy simulation. It'll be combines the SST with the LES. So the actual parameters, it was a 6.7 meters per second airflow at 295 Kelvin. And then a constant heating of about 100 watts around the entire heated cylinder. This gives us a Reynolds number, 1170, about the diameter, which is enough to be considered turbulent. And so we have a 10% feed turbulence level, which is not what they reported, and we didn't find out until a week ago. So they actually used a 0.1% turbulence level, so that will be reflected as well. But going into the actual results, the velocity validation, we normalize about the same equations that they did with this U prime. The UE is the free stream velocity, with the UO being the difference between the UE and the U, which is just your velocity. and then eta being the difference between the wide plane going from that middle of the heated cylinder up into the about 2.5 away, so pretty much into where we're going into the free stream now. But you can see here that SST closely follows the experimental results. LES does not, and IDDS is in between. Seeing a little bit further into this, you can see that it's very close towards the beginning, and then as we go further away from the middle of the plane, they diverge more. This is most likely due to how the turbulence was working out between the two, and the various heat dissipation was different. But going into our temperature validation, we again use the same thing. It has the same sort of stuff with TE being the free stream, TL being the difference. SST, once again, being the closest. LES is not. IDDS is in the middle. But going into some of the relative errors between them. And then going into our velocity contours. So SST, we can see that it averages out all the results, illustrating the consequences of this heated obstacle in the way. LES, we can see, has turbulence in the wake of the cylinder in this instantaneous velocity contour. So we can see all the variations. And then IDS still has some turbulence, but it is more evened out. And then the similarity between all the different close-ups of this can also indicate that our mesh needs refinement. But going into the temperature contours, the SST displays a higher temperature tail in the backflow of the heated cylinder. The LES has a shorter tail following the cylinder than the SST, with more dissertations falling further downstream of this. IDDS, once again, in the middle. And going in between these two, you can see that SST has a much greater region that it is being influenced by the temperature change, with the LES just having that little bit of area that it's actually influencing. So pressure contours, we have the average pressure gradient with an adverse pressure gradient following the heated cylinder, causing vorticity after the cylinder. The LES shows a lot of variation afterwards. You can see that like darker blue and aqua, all those mixing in between together, causing vorticity. And then IDDS actually is following more closely to SST than LES just for the pressure gradient. As you can see with this part, like it still has some variation, but the general flow of it models after SST. And then we started exploring a bit into the turbulent energy contours. SST has the average of it, of the influence of the heated cylinder. And then IDDS is quite different from SST. You can see even here that the whole magnitude of IDDS is shifted from SST and has much smaller magnitude than the SST. But then we have some heat flux profiles. These were just looking into LES and IDDS because of the fact that SST averages everything out. So you can't look for a difference if it's all averaged. But we once again followed their equations for normalizing everything. But the LES has a steeper curve and higher max value due to the resolution of turbulence. IDDS has a smoother curve, as it is affected by the equations it does share with SST. And then looking into some of the relative difference, even though like in the middle it looks pretty clear, and then towards the end they are a lot different. The relative difference between them actually is quite high towards the end. But in conclusion, going over our summary, SST provided data that followed the same behaviors seen in the experiment. LES was the least accurate because its numerical analysis accounted for turbulence a lot more, and it depends a lot more heavily on its mesh. IDDS combined the accuracy of SST with the turbulent behavior seen in LES while saving on computational power. Seen a little bit further here, that 10% free stream turbulence versus the 0.1% and the refinement of mesh is where we can see a lot of this difference. And you can see kind of here just the U-naught difference, the relative error, or the error that the experiment by Antonia and Brown said they had a 10% difference when getting all their extractions. So we're looking at being around that 10% region. SST, it's got that. IDDS is at that 20%, so it is double, but we foresee once we use the refined mesh that this will decrease drastically. And maybe if we use, correct variables and parameters, that would also help. But going into the next steps, pursue further refinement with the meshes for more accurate results. And then we can also test mesh independence since we already have it. Investigate other heat dissipation related parameters. We kind of went into it a little bit with our turbulent kinetic energy and our heat flux, but we would like to pursue even further, being able to look more closely into how this heated cylinder affects the wake downstream. And then after that, we can continue messing around with this model once the validation goes through. So we have our feed turbulence levels, feed air velocity, fluid type, heated cylindrical materials. We foresee a lot of future research being able to be done with this, and we like to pursue it further. But you can check out our other research after hearing two of us. But that is the end, unless there are questions. Oh, oh.
So how long did it take to run your simulations? Was there a relative difference depending on the model you selected?
SST was the one that we were like pursuing first because we knew it would be the least amount of time, and that one took like a day and a half, I would say, with all of our beginning stuff. And then SST and LES with just this course grid was taking like 2 to 3 days. We ran those at the same time, so.
Do you know the construct using the experimental results so that you can see that
I mentioned it a little bit while I was talking about UL, but they said they had a 10% when they were measuring with their data. So.
So was the LES done on the same 2D mesh, or was it a three-dimensional mesh that you created for the LES?
It was a three-dimensional mesh used for everything.
Oh, everything. Okay.
Yes.
So when did you start averaging the LES? You reported velocities, for instance, of those kind of fluctuating moments. So when did you start averaging? I guess what were your initial conditions? Did you use the RANs to initialize the LES, or was it just a zero?
We just used from zero. So it was like LES had its own separate modelings that it just had that 6.7 meters per second velocity.
So did you start averaging, when did you start the reported velocity? I'm going to average the LES over time. When did you start that window?
I would say was not done as well as it could have. It definitely could use a bit more, but we did it until it like the convergence decreased, and then we took like some off the end. So I don't have an exact number, but yeah.
Did you compare the results of LES and IDDS to SSDS and the average profile contours?
Yeah, so all the contours were instantaneous, but the various profiles were averaged.
Only profile.
Yes. So the contours were used more for instantaneous to really see the turbulence difference between SST and the others.